Alrighty, so good afternoon. It is nice to be back in the classroom. It's nice to have students back in the classroom. I'm glad to not be on quarantine anymore. That is really nice. I hope you all had a good weekend. Many of you I talked to yesterday as well with our weekly lesson. So it's nice to see you all again. Today we're going to get started. I just want to go over a couple of things in Canvas because I've added some stuff into Canvas to help review and such. So I'm going to go over those things and we will begin our chapter 11. So I'm going to share my screen. Do that way. Yeah. All right. Go away. Oh. All right, so hopefully on the shared screen you can see the Canvas course. On here, what I want to point out is I've added some stuff to some modules and added some modules to what we already have access to. In the things you might need section, I've added the directions, that PowerPoint presentation on how to kind of get ready for the AP digital exams. So if you are taking AP exams digitally and you haven't gotten the app, you haven't gone through that process yet, please look through that so you know what to do. I also have the PowerPoint of the review from chapters 1, 2, 4 through 10 that we did last week that we did not have an opportunity to get through all of it. So that is available if you'd like to look through all of those slides as a review. It didn't necessarily fit into a specific module, so I put it there. And then I added the AP Classroom Review Materials module. This has links to review videos that were produced by College Board and AP. They're a little bit longer than the AP Daily videos. They're about 45 minutes a piece, but it breaks kind of everything down by kind of major topic area for the tests. So if there's something that you're not getting a good grasp of yet, or you just want to review that main area, these would be a good resource for that. All right, and these I believe are actually YouTube videos, so they work on more platforms more cooperatively than the AP Daily videos. Right, and then chapter 10, we're pretty much, we've completed chapter 10, so that module's there. You should hopefully be working through the assessments. And then here we have essentially the last module. I'm combining chapters 11, 12, and 3, the 3 chapters we haven't done yet, into the final, last unit. So hopefully this works out as a positive thing. The idea is that this way there will only be one more free response question assessment and one more multiple choice assessment for the entire year, as far as this course is concerned, rather than trying to have 3 more, right? We basically have 4.5 weeks of school left. That would be kind of crazy. So we're not doing that. So we're combining this into one final unit. There will be one kind of cumulative for chapters 11, 12, and 3 assessment that's free response question and one multiple choice. All right, so that means there will only be 2 more required assignments essentially for the rest of the year. There will be our classroom participation things. Right, but as far as those major assessments, there's just going to be 2 more. So hopefully that works out to not add a whole lot more to your all's workload. All right, so that's kind of the idea. I have most of the resources ready for chapter 11, which we are starting today. I'm working on the study guide and practice problems, which I do not have finished yet, but most of the resources are all ready, right? In our notes and resources for 11.1, we have the PowerPoint presentation, which I'll do today. Right, we have the links to the AP Daily videos that have to do with the chapter 11.1. For section 11.1, we have some worked examples from the book and the calculator directions on how to do some of the things from this section on your calculator. And obviously the textbook section. The same things are available for section 11.2. I'm almost done with the study guide for section 11.1, and I'll update that once it's ready, but all of the The 2 study guides and practice problem solutions should all be ready by the end of the week. All right, and so most of the stuff for chapter 11 will be available soon. So there's some things in Canvas to update you guys on what's there. And yeah, so there's that. So that brings us to the lesson. All right. Come on, yeah, it's working. So we're gonna start chapter 11 today, which essentially chapter 11 is dealing with more significance tests, right? Except now we're doing inference for distributions of categorical data. Most of what we've been doing recently has been dealing with quantitative data, right? Things that have means and standard deviations and ways for us to standardize them that make sense with quantitative data. Categorical data, we don't get those same things to use, so we have to use a different type of test. That's what we're going to get introduced to today. And so if you are taking notes, you should have that ready to write some stuff down if that so pleases you. All right, so here we go. Hopefully this will cooperate. Yeah. All right, here we go. So the objectives for today, we want to be able to state appropriate hypotheses and compute expected counts for a chi-square test of goodness of fit. We'll discuss what goodness of fit means, what that is momentarily. We need to calculate the chi-square statistic, degrees of freedom, and p-value for a chi-square test of goodness of fit, and perform a chi-square test for goodness of fit. Essentially, that third check mark is everything in the first 2 check marks put together. Lastly, we want to be able to conduct a follow-up analysis when the results of a chi-square test are statistically significant. We will talk about this in another lesson. It's not necessarily covered in this presentation. I'm not sure why the authors decided to put that objective in here when they don't talk about it. But nonetheless, here we are. So sometimes we want to examine the distribution of a single categorical variable in a population. Right? The example they're going to use here is the mixture of M&Ms. Right? We get a bag of M&Ms. What's the distribution of the colors? Right? The categorical variable is the color of the M&M. And the chi-square goodness of fit test allows us to determine whether a hypothesized distribution seems valid. In other words, it allows us to determine if what the company says the distribution is of the different colors is actually true. Or do we have evidence of the contrary, saying that what they say the proportion is not what it is? We can decide whether the distribution of a categorical variable differs for 2 or more populations or treatments using a chi-square test for homogeneity. That will be in another section. That's a next lesson kind of thing. Right? Today's lesson focuses on this top paragraph here. Goodness of fit test, that's where we're focusing. We can also do a chi-square test for homogeneity when we're comparing 2 or more populations or treatments. All right. We will often organize our data in a 2-way table. We've seen 2-way tables in previous sections. It is also possible to use the information in a 2-way table to study the relationship between 2 categorical variables. Right? In other words, is there an association between the 2 variables or are they independent? The chi-square test for independence, which is another way of using our chi-square statistic, which we'll get to later today, right, allows us to determine if there is convincing evidence of an association between the variables in the population at large. So our chi-square statistic and our chi-square tests can be used in 3 different scenarios. Right, we're going to focus on today the chi-square goodness of fit test, that first paragraph. And in the next section, we cover the chi-square test for homogeneity or independence. Okay. So Mars Incorporated makes milk chocolate candies. Here's what the company's Consumer Affairs Department says about the color distribution of its M&M's milk chocolate candies. On average, the new mix of colors of M&M's milk chocolate candies will contain 13% of each of the browns and reds, 14% yellows, 16% greens, 20% oranges, and 24% blues. Our one-way table there at the bottom summarizes the data from a sample bag of M&Ms, milk chocolate candies. In general, one-way tables display the distribution of a categorical variable for the individuals in a sample. So the individuals in the sample are the M&Ms. We have a sample size of one bag which has 60 M&Ms, and we have the count of each color on our table. 9 blue, 8 orange, 12 green, 15 yellow, 10 red, and 6 brown. There is a reason why we're using counts, which we'll discuss later, and not proportions, considering that we're talking about percentages in the first paragraph. Right, but we'll make sense of this in a moment. Right? If we wanted to, we could find the sample proportion of blue M&Ms, which is p hat equaling 9 over 60 equals 0.15. This is 9 divided by 60. Right? Which is now up at the top of the screen. Since the company claims that 24% of all M&Ms milk chocolate candies are blue, we might believe that something fishy is going on because 24% is not 15%. Right? We could use the one sample z-test for proportion to test the hypothesis, as we did in chapter 9. We have the null hypothesis, p equals 0.24, the alternative that p is not equal to 0.24, where p is the true population proportion of blue M&Ms. We could then perform additional significance tests for each of the remaining colors. We would have to do this for each of the remaining colors if we're doing it this way, because we're concerned about the entire distribution. Right? We're not just worried about are they correct about blue M&Ms, we're wondering are they correct about all of the distribution. So if we want to use a one sample z-test, we would do it for blue, orange, green, yellow, red, brown, and check them all. Performing a one sample z-test for each proportion would be pretty inefficient and would lead to the problem of multiple comparisons. We'd get varying results. We might find significance for blue and say that, well, then, you know, we have evidence for the alternative for blue, but then maybe not for orange, and then maybe not for green, but then we would find significance for yellow. So what would we do at that point if we have conflicting conclusions? Right? We have multiple comparisons of the same kind of idea. It just doesn't work out. So performing one sample z-test for each color wouldn't tell us how likely it is to get a random sample of 60 candies with a color distribution that differs as much from the one claimed by the company as this bag does, taking all of the colors into consideration at one time. For that, we need a new kind of significance test called the chi-square goodness of fit. How well does our sample fit into the proposed proportion? Right, our null hypothesis is a chi-square goodness of fit test should state a claim about a distribution of a single categorical variable in the population of interest. And so we have that here. The null hypothesis is that the company's stated color distribution for M&M's milk chocolate candies is correct. Right? I'm going to say, okay, they're right. The alternative hypothesis in a chi-square goodness of fit test is that the categorical variable does not have the specified distribution, which is as simple as essentially saying the same statement but ending with not correct. Right? It's almost easier to write these types of hypotheses than what we did previously because we actually don't need to have a parameter defined necessarily. Right? There's like less steps to writing it. Right? So we get the alternative. The company's stated color distribution for M&M's milk chocolate candies is not correct. So this is how we can write our hypotheses for our goodness of fit test. Is there anything I can clarify so far? Or does anyone need a moment to write anything down? We could also write the hypotheses in symbols as h sub 0, such that P blue is 0.24, P orange 0.2, P green 0.16, P yellow 0.14, P red 0.13, P brown 0.13. And the alternative, at least one of the P sub i's is incorrect, where the little subscript I is a placeholder for whatever color we're talking about. At least one of the colors is incorrect. where P sub color equals the true population proportion of M&M's, milk chocolate candies of that color. So we could write our hypothesis this way. In my opinion, there's just more that could go wrong in writing it this way. There's more things to be judged on if you write it this way. The idea of the chi-square goodness of fit test is this. We compare the observed counts from our sample with the counts that would be expected if the null hypothesis is true. Notice again, we're talking about the count. How many of each color of M&M did we see? We're not talking about proportion here. The more observed counts differ from the expected counts, again, counts, the more evidence we have against the null hypothesis. Assuming that the color distribution stated by Mars Inc. is true, 24% of all M&M's milk chocolate candies produced are blue. For random samples of 60 candies, the average number of blue M&Ms should be 0.24 times 60, which equals 14.4. And this is kind of similar to what we did when we were dealing with random variables and finding our probability distributions. We just took each possible value that our random variable could take times the probability of that thing happening. In this case, it's probability of each color times the sample size. So it's the same kind of idea. Right? And this is our expected count of blue M&Ms. Using this same method, we can find the expected counts for the other color categories. Like this. So we get orange, green, yellow, red, and brown, 12, 9.6, 8.4, 7.8, 7.8. So this is what we would expect if we sampled 60 candies over and over and over again. We would expect to average per sample of 60, 12 orange, 9.6 green, 8.4 yellow, 7.8 red, 7.8 brown, and 14.4 blue. When we compare this to what we observed, we see a difference just by looking at the observed versus the expected. 9 is not the same as 14.4, right? We have a difference that we can clearly see. This essentially says, okay, well, I can continue with doing this test because my preliminary look at this evidence says that there's probably a difference. Is there anything I can clarify about this screen? To see if the data give convincing evidence against the null hypothesis, we compare the observed counts from our sample with the expected counts, assuming the null hypothesis is true. If the observed counts are far from the expected counts, that's the evidence we are seeking. So here's one way we can also compare this besides using our table. We can do a side-by-side bar graph, because bar graphs are what we use with categorical data. And we can easily see that some of the bars are they have a difference between within the colors, right? The expected is much greater than the observed for blue. And then we have our expected is lower for yellow than observed, right? So we can see clear differences. Right? We see some fairly large differences between the observed and expected counts in several color categories. How likely is it that differences this large or larger would occur just by chance in random samples of size 60 from the population distribution claimed by Mars Incorporated? This is a very similar question that we're answering when we're talking about p-values. The p-value is essentially finding out the probability of getting the results that we saw in our sample if our null hypothesis is true. To answer this question, we calculate a statistic that measures how far apart the observed and expected counts are. The statistic we use to make the comparison is the chi-square statistic. And this is what it looks like. The chi-square statistic is a measure of how far the observed counts are from the expected counts. The formula for the statistic is chi-squared. Chi is a Greek letter, it looks like an X. It is pronounced chi. Equals the sum of the observed minus the expected squared divided by expected. Essentially, we can think of this as the standard deviation for our categorical data. Right? When we're dealing with standard deviations and quantitative data, the standard deviation tells us how far away we are from the mean or expected value. The chi-squared statistic serves the same purpose. Except now we get to use this with categorical data because we cannot calculate a standard deviation with this, where the sum is over all possible values of the categorical variable. All possible counts, essentially. So this is our how far away are we from what we expect statistic. Oh, sorry. Does anyone need a moment to write this down? Raise your hand. The table shows the observed and expected counts for our sample of 60 M&Ms milk chocolate candies. We're going to calculate the chi-square statistic. The same table we saw previously. And here is our calculation, which also shows where each of those fractions came from. So we take the sum of these 6 fractions, because we have 6 colors, 6 categories within our categorical variable. Right, so this first fraction here is from our color blue. Right, we saw 9 blue M&Ms. The expected was 14.4. 9 minus 14.4 squared divided by 14.4 gives us our first value, and then so on for the rest. We ultimately get a chi-square equaling 10.180. Think of chi-squared as a measure of the distance of the observed counts from the expected counts. Large values of chi-square are stronger evidence against the null hypothesis because they say that the observed counts are far from what we would expect if the null hypothesis were true. Small values of chi-square suggest the data are consistent with the null hypothesis. So similarly to like a standard deviation, a large standard deviation means that our data is very spread out. A small one means that it's less spread out. Right? In this case, a large chi-square says that this is very different than what we expect. Small says it's very similar to what we expect. The sampling distribution of the chi-square statistic is not a normal distribution. It is a right-skewed distribution that allows only positive values because chi-squared can never be negative. When the expected counts are all at least 5, the sampling distribution of the chi-square statistic is close to a chi-square distribution with degrees of freedom equal to the number of categories minus 1. Okay, and so we get the chi-square distributions. Chi-square distributions are family distributions that take only positive values and are skewed to the right. A particular chi-square distribution is specified by giving its degrees of freedom. The chi-square goodness of fit test uses the chi-square distribution with degrees of freedom equaling the number of categories minus 1. Right? The sample size does not matter for our degrees of freedom here. It all depends on how many categories are in our categorical variable. We computed the chi-square statistic for our sample of 60 M&Ms to be chi-squared equaling 10.180. Because all the expected counts are at least 5, the chi-square statistic will follow a chi-square distribution with degrees of freedom 6 minus 1 equaling 5. Reasonably well when the null hypothesis is true. So we have the little distribution here, the chi-square distribution with degrees of freedom 5. Our chi-square statistic, 10.18, lies right here. And this shaded area is the proportion under the curve greater than that value. Okay. To find the p-value, we use table C, the only table in the tables and formulas packet that we have not used, and look in the degree of freedom equaling 5 row, which we have a little excerpt of right here. So our degree of freedom 5 rows here. We're going to follow this. Obviously, there are more columns than what's shown here, but 10.180 lies between 9.24 and 11.07. Right, which means our p-value is between 0.05 and 0.1. So kind of like table B, we're not going to land on an exact p-value when we take our statistic back to the table. Right, since our p-value is between 0.05 and 0.1, it is greater than alpha equaling 0.05. Right, and again, it never stated that we're using a significance level of 0.05, but since none was given, we default to use 0.05. That is just the automatic default. If you're not told what significance level to use in a significance test, use alpha equals 0.05. Therefore, we fail to reject the null hypothesis. We don't have sufficient evidence to conclude that the company's claimed color distribution is incorrect. Is there anything I can clarify here? Any questions? So just as every other inference we've done, there's conditions before we can do this type of thing. All right, so our conditions for performing a chi-square test for goodness of fit is that it is random. The data come from a well-designed random sample or from a randomized experiment. That the 10% condition is met when sampling without replacement. We need to make sure that our sample size is less than 10% of the entire population size. And we must do our large counts condition, which in this case is saying that all expected counts are greater than 5. Right? And that is a greater than, not at least. Right? That is a strict inequality, meaning it must be greater than 5, not equal to. Before we start using the chi-square goodness of fit test, we have 2 important cautions to offer. 1, the chi-square test statistic compares observed and expected counts. Don't try to perform calculations with the observed and expected proportions in each category. You will get horribly, horribly wrong solutions. When checking the large sample size condition, be sure to examine the expected counts, not the observed counts. Does anyone need a moment to write any of this down? Please raise your hand. And so then this is how we carry out a chi-square test for goodness of fit. Suppose the conditions are met. To determine whether a categorical variable has a specified distribution in the population of interest, expressed as the proportion of individuals falling into each possible category, perform a test of the null hypothesis that the stated distribution of the categorical variable in the population of interest is correct, versus the alternative hypothesis that the stated distribution of the categorical variable in the population of interest is not correct. So a lot of repeating a lot of the same thing and then just changing correct to not correct. Start by finding the expected count for each category, assuming that the null hypothesis is true. Then calculate the chi-square statistic. Chi-squared equals the sum of the observed minus expected squared divided by expected, where the sum is over the k different categories. K is a variable representing the number of categories. The p-value is the area to the right of chi-squared under the density curve of the chi-square distribution with k minus 1 degrees of freedom. All right. So this is the general idea for how to do a chi-square test for goodness of fit. Is there anything I can clarify? Does anyone need a moment to write anything down? Please raise your hand. So let's look at an example doing the entire process. And this is a test for equal proportions. So in his book, Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. Specifically, January 1 is the cutoff date for youth leagues in Canada, where many NHL players come from. Players born in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. To see if birth date is related to success, judged by whether a player makes it into the NHL, a random sample of 80 NHL players from a recent season was selected and their birthdays were recorded. The one-way table below summarizes the data on birthdays for these 80 players. Notice they broke the birthdays down into quarters. So we have the first 3 months of the year, January through March, second 3 months, third 3 months, fourth 3 months. So we have 4 categories for this variable, and then the number of players for each category. Do these data provide convincing evidence that the birthdays of all NHL players are evenly distributed among the 4 quarters of the year? And so begins our 4-step process. And any inference involves a 4-step process. So we state we want to perform a test of the null hypothesis. The birthdays of all NHL players are evenly distributed among the 4 quarters of the year versus the alternative that the birthdays of all NHL players are not evenly distributed among the 4 quarters of the year. No significance level was specified, so we'll use an alpha equaling 0.05. Next step 2, we need to plan. If the conditions are met, we'll perform a chi-square test for goodness of fit. Random, the data come from a random sample of NHL players. We were told that in the context. 10%, because we are sampling without replacement, there must be at least 10 times 80 equaling 800 NHL players. In the season when the data were collected, there were 879 NHL players, so we're good to go. Large counts. If birthdays are evenly distributed across the 4 quarters of the year, then the expected counts are all 80 times 1 quarter equaling 20. These counts are all at least 5, so our large counts condition has been satisfied. Next, we do the math. We need to calculate our test statistic. In this case, chi-squared equals 32 minus 20 squared over 20, 20 minus 20 squared over 20, 16 minus 20 squared over 20, and 12 minus 20 squared over 20, which ultimately equals 11.2. Here's a little illustration of that distribution with the chi-squared distribution of degrees of freedom equaling 3. The degrees of freedom are 3 because we have 4 categories. 4 minus 1 is 3. And we see our chi-squared statistic falls right here on our distribution. And our p-value is this little sliver over here to the right. As the excerpt shows, chi-squared corresponds to a p-value between 0.01 and 0.02. Right, and that is because 11.2 falls between 9.84 and 11.34. It's closer to 11.34, so we can assume that our p-value is probably closer to 0.01 than it is to 0.02. Right? Either way, it's greater than 0.01 and less than 0.02. So anything I can clarify about the calculation step here, the do step? Then we finally conclude. Because the p-value, 0.011, which they did not show, but I'm assuming they used the calculator to get an exact p-value, which we can do, is less than alpha equaling 0.05. We reject the null hypothesis. We have convincing evidence that the birthdays of NHL players are not evenly distributed across the 4 quarters of the year. Is there anything I can clarify or explain about this example? So that brings us to the end of this presentation. Right, we covered those first 3 check marks. The follow-up analysis is something that I'll cover later. It's not included in this slide, but it's not a huge thing. I'll include it in what we do next. So with that's the end of that. Let me stop sharing my screen. There we go, I think. All right, so that's the lesson for chi-square tests for goodness of fit. Right, this is what we'll be practicing tomorrow in class. I've got a Desmos activity set up for us to practice finding expected counts, comparing that to the observed, finding our test statistic, p-value, degrees of freedom, making a conclusion, all that fun stuff we're going to get practice with tomorrow during class. Yeah. Does anyone have any other questions, comments, concerns before I end class? All right. Well, then that is all that I have for today. I hope you all have a great rest of your day, and I will see you tomorrow.